So to recap, our equations for objects that are oscillating look like this. X of t equals x max times the sine of 2 pi ft. V of t is equal to the maximum velocity times the cosine of 2 pi ft. And our acceleration is equal to minus a max times the sine of 2 pi ft. So for those of you who have had calculus, you will notice that there is a, if we're just looking at the trig functions here, the velocity, the cosine, is the derivative of the sine. We won't go into more detail than that, but there is a good calculus relationship between these things. So we would like to know now, how are these values related to one another? If I pull this back, so if I give this some small amplitude oscillation, x max is small, only a centimeter or something, and the velocity, the maximum velocity it reaches is pretty low. But if I give this a bigger amplitude oscillation, it also has a higher maximum velocity. So these are related, and we would like to figure out how these values are related. Okay, so in order to do this, I want to think about energy. So in our little cartoon of what's going on, if we think about pulling our mass and stretching the spring, and I want to convince you that we can ignore gravitational potential energy during this. It's not going to make a difference, and maybe to make that easier, we should think about things moving horizontally. Since I've claimed this whole time that the equations are the same if we have a mass and spring moving horizontally. So let's think about that. So I have this mass and a spring attached to it, and the spring is attached to like the wall over here. So if I pull this mass to the right and stretch the spring, like right before I let it go, I have stored a lot of potential energy in the spring, but at that moment, my kinetic energy is equal to 0, right? I've stored kinetic energy, sorry, it's capital K kinetic energy, U potential, sorry. Our U is not 0. We have potential energy stored in the spring. Our kinetic energy is 0 because this is at rest. So if we let it go now, our mass is going to accelerate to the left. It's going to have some velocity, right? So it's going to have some kinetic energy K. But when it's at the equilibrium position, at the equilibrium length of the spring, our potential energy is equal to 0. So in other words, we start out with energy that's potential and not kinetic. We end here with energy that's kinetic and not potential. And what's important here is this is our furthest position, x max. And this velocity here is our highest velocity, v max, when we have no potential energy left. So if energy is conserved, if the amount of energy in this picture is equal to the amount of energy in this picture, that gives us a way to figure out what's going on. So here, our total energy is equal to 1/2 k delta x squared. So this is our spring constant k. And delta x, how far we are from equilibrium, is just x max. So this is 1/2 times our spring constant times x max squared. Here, our energy is all kinetic energy. So this is 1/2 mv squared, and our potential energy is 0. And this velocity, as I just said, is v max. So if energy is conserved, then 1/2 k x max squared is equal to 1/2 m v max squared. So now we can solve for Vmax in terms of Xmax. So let's do that. Our 1/2, multiply both sides by 2, our 1/2s cancel. If I divide both sides by m, I get Vmax squared equals k over m x max squared, and now taking the square root, I get V max equals the square root of k over m times x max. So that's kind of useful. That tells us the relationship between those two. We might see that this square root of k over m looks familiar, right? This is not the first time that's shown up in this class. In fact, if you remember in particular, the frequency of oscillation of this system is 1 over 2 pi root k over m. So root k over m is equal to 2 pi times f. And in fact, so this equation we did is true just for the spring system, but it's true for any system that Vmax is equal to 2 pi f times x max, for any oscillating system. So depending on whether we know the frequency or whether we know the spring constant in mass, we can figure out the relationship between this maximum velocity and the maximum position. All right. Cool. I will erase this. I'll leave this up for now. We also can do a similar thing to figure out the acceleration, although here we're not going to use energy, we're going to look at forces. So when we have our block pulled back its furthest distance from its equilibrium position at x max, the acceleration that we get is equal to f over m, or I guess I should say a max is equal to f max over m. And the maximum force we get, if we've pulled this back a distance x max, is equal to this distance x times the spring constant. So this is k x max over m. So in other words, a max is equal to k over m times x max, which is another factor of the square root of k over m, or another factor of 2 pi f. So this is equal to 2 pi f squared times x max. So these two equations we can also use to figure out the relationship between acceleration and position. All right, so like I said, these equations with k and m, these are only good for our mass spring system, but these 2 pi f ones we can use for any system, including our pendulum system, or anything else oscillating where we know its frequency.